Yeah. So in routing strategies, we actually have a dynamic routing. We discussed it in last lecture as well, just for the revision purpose. We will have a fixed routing that will be permanently and no change will be possible over there in the route. In virtual circuit, we have a temporary connection with the destination node, and that is actually for predefined duration or for the time. And similarly, dynamic routing, which is actually as per condition, you can change, you can switch, you can shift to any other channel whenever there is any disturbance, any issue like congestion, like overhead, like security. So you can change the connection in this routing strategy at any time. Next is the connection strategy, that how your connection would be. So the first one here is the circuit switching, in which a permanent physical link is established for the duration of communication. And you have look in the fixed routing strategy as well, that over there we also have a fixed link between source and destination. And here the example they are giving is the telephone system. So if you look at the telephone system, there is a cable uh, connectivity between 2 points, between source and destination, but it doesn't mean that the connection is always established over there. Still, you have to dial the number, and then onward you have to wait for the response, and then the bell will ring at the receiver or at the destination site. The next one here is message switching, where a temporary link is established for the duration of one message transfer. And if you look at this, the message is actually a block of data that you can transfer. And over here, he is giving the post office mailing system in the example. As you are going to send a letter to someone, you have to write the letter, put it in the envelope, and then put it in the post office mailbox. And then the post office or the post or you can say the postman is actually responsible to take it from there and deliver it to final destination. So same is the case with the message switching, that it is a kind of uh, block of data. The next one is packet switching, where messages of variable lengths are divided into fixed length packets, which are sent to the destination. So over here, if you see that you have different types of packets, and there is a possibility that every packet should follow a different route to access the destination node. Each packet may take a different path. Look at this. Each packet may take a different path to the destination network, and therefore the packet must be reassembled. The packet must be reassembled when they get the destination node. As I discussed in the last lecture as well, that you have to change the arrangement of your packets, because there is possibility of out of order delivery as well. There is possibility of out of order delivery as well. And let me give you an example over here on the whiteboard. So look at this. You have these small packets, and 1, 2, 3, 4, and 5. I also explained last time, and there are multiple links from this source to destination. So So look at this. There are three ways over here to access this destination node. So this destination node is accessible by route 1, 2, and 3. And we have 5 packets. So if we send 1 from here, 2 from here, 3 from here, and then again 4 from here, and 5 from here, and there is any blockage or any congestion over here, then there is possibility that we can get out of order data delivery. Like 5 is received first, then onward 3 is received, then onward 2 is received, and then 4 is received, and then 1 is received. So this is actually the arrangement in which we have received these packets as destination node. So that's why the overhead will be increased here, is the destination node will organize these packets in its actual form to process them. Similarly, circuit switching requires setup time. Look at this. Circuit switching requires setup time but incur less overhead for shipping each message and may waste network bandwidth as well. While message and packet switching incur more overhead per messages over here. So look at this, that you have initially, let me explain it here again. So look at this, that is in TCP protocol, we have two people and first they establish a connection. So it's like this, that there are two people and they are communicating with one another, and they are here on different mountains. You can say this as an example. And he is saying that, are you listening me? He is saying, are you listening me? And similarly, over here, he will respond that, yes, I am listening you. And then he will repeat the same question, are you listening me? And then onward, he will reply with yes. And after that, it means the connection is established and now they can transfer data with one another. Connection established, and now they can transfer data with one another. So if you look at this, there is initially some overhead in this connection establishment process. This is overhead of connection establishment. While in other way, you can see that in message passing, there is no such limitation that you will establish no connection and blindly forwarded. Blindly send data on different links. So actually this is actually the packet switching and the circuit switching. There is also a contention strategy, as there is a competition between these nodes at several sites. They want to send their data, they want to transfer their data, and that's why they are looking for connectivity with the destination node. So there is a single link and they want to transfer their data. Therefore, to avoid any collision or to resolve this contention, we are using this protocol as CSMA CD. And over here, let me explain it. Here in the next strategy, you can say that we have these computers connected with these this is a kind of bus topology. So we have computer 1, 2, 3, 4, 5, and 6, and they want to send something here to this server. So now if they want to put their data or packet on this link, then there is possibility of collision, or there is a possibility of a contention between these nodes that who will access. That's why we have to design a protocol to look into this matter, and we have to define the strategy as well, that which one will send first, which one will send second, which one will send third, then fourth, then fifth, and then sixth. So this is actually the mechanism in the CSMA CD, that is carrier sense multiple access collision detection. So first every node should sense the media, that either the media is free, and if the media is free they are able to send. If media is busy, then they have to wait. So that is actually the mechanism they are going to follow here in this protocol. Now look at this. In carrier sense, with multiple access collision detection, a site determines whether another message is currently being transmitted over the link. If there is any transmission on the link, then there is 100%, yeah, maximum possibility that the packet he is sending will collide with the existing packet on the link, and there will be no data delivery to the destination node. If two or more sites begin transmitting at exactly the same time, then they will register a CD, that is collision detection, and will stop transmitting. Look at this. If you even tried to access the media, then the media is busy, then there will be collision. So you have to stop the possibility of collision. You have to stop the possibility of collision with the help of stopping your data, your data and your packets. When the system is very busy, many collision may occur, and thus the performance may be degraded. Whenever there is such a system, then there is a possibility that the system may degrade. See, SMA-CD is used successfully in Ethernet. Look at this, it is very successful to be used in Ethernet. However, there is another possibility here that let me explain it over here, that for example, there are two nodes and they want to access this communication link at the same time. Look at this. And look at the time over here. The time is 10 a.m. Look at this. Computer number 1 and computer number 2 both sense the system. Sense the system at 10 a.m. and the link or the system or the network is free at 10 a.m. Then in next clock pulse, that is 10:01, they attempt to transfer, attempt to send data. Is they attempt to send data and their data reach to this link at 10:02, then there is collision between 1 and 2 packets. So look at this. There is possibility that both of these nodes, when they sense data at 10 a.m., the link was free. But when they transferred their data, then the collision happened. So there are some scenario in which maybe you are fully following this protocol of carrier sense multiple access. You sense the link and then onward you transfer it, but still the possibility of collision is there when two nodes attempt at the same time to sense the link and then transfer their data in same clock pulse. The next one to resolve this issue of contention is token passing. A token is continuously circulate in the system, usually in the form of a ring, and a token is actually like a pass. Whenever you have that token, you can transfer this data. A site that want to transmit information must wait until the token arrive. Look at this, you cannot transfer your data unless and until you have received this token. Sometimes there is a competition on the token timing as well. That's why there is another algorithm in which you define the time of this token, that for how long every node can have this token. It can be 5 minutes, it can be 2 minutes, it can be 3 minutes, it can be 10 minutes. If someone, for example, if the token time is 5 minutes and someone have more time to transfer data, then he has to wait for its next turn to complete the transferring of your data to the destination node. If he is not, if he is able to transfer data within that predefined time of token with the user, like 5 minutes, then he can do so and transfer the data. When the site completes its round of message passing, it retransmits the token. Look at this, when they complete, then they are bound. This is actually, they are legally bound in this protocol. Then when they complete their time slot, number one, when they complete their data transmission, then they have to release the token, that the token should go to the next node. Similarly, we have the message slot. A number of 6 length message slots continuously circulate in the system. A number of fixed slot continuously actually revolve inside your system in the form of ring, and this is just like a cabin in which you can put your data. You can put your data and you can transfer it, or you can about uh, the carriage system, in which you put your data in a carrier, and the carrier will take it to the next destination, to the next point, or to the final destination. Since a slot can contain only fixed side messages, a single logical message may have to be broken down into a number of smaller packets. Look at this, if even your data or your block is bigger than the message slot, then it will be divided into small parts, and each of which is sent in a separate slot, and then you have to send it in a separate slot. Let me explain it over here on the board, on the whiteboard. So look at this, we have a big block, and we are actually unable to transfer it into small parts into the message slot. That's why we have to divide it into small parts, that is A, B, C, D, and E. And here is the node who will transfer it. So here is the destination node, this one is the sender node, and this one is the destination node. So look at this, they will transfer it. This is, like as we told you, a message slot. So he will first put A in this, then in next slot he will put B, then in next he will put C, and will transfer one by one. While this is actually a single message. This is message number 2. For example, this is message number 2. So now if he want to send it, so this recognition of this A will be to A, it will be to B, it will be to C, this will be to D, and then to E. So he will transfer these packets here to the destination node, and he will receive it into this form: to A, to B, to C, to D, to E, And now onward, this is responsibility of the destination node to combine all those frame into one part, and he will get this single block of data. And this process is actually called fragmentation and reassembly process. This is called segmentation and reassembly process. So this fragmentation and reassembly process is actually taking place at transport layer. This process actually takes place in transport layer, and then this increased overhead on the destination node. This increased overhead on this destination node, that the destination node will take this much burden or this much time to reassemble this data, and will create a complete packet of packet number 2 from the small frames. Okay, next is the communication protocol. The communication network is participated into the following multiple layers. Look at this, we have a complete setup to establish this connectivity process between distributed system. And there are multiple layers operating that is belonging to the OSI model. Actually, these layer belongs to OSI model, and every layer is responsible for different type of activities. Like in physical layer, it handles the mechanical and electrical details of the physical transmission of a bit stream. And similarly, the data link layer, which handles the frames or fixed parts of packets, including any error detection and recovery that occurred in the physical layer. I will explain it on the board as well. Similarly, in the network layer, it provides connections and route packets in the communication network, include handling the address of outgoing packets, decoding the address of incoming packets, and similarly maintaining the route information for proper response to changing load levels as well. So moving back to the whiteboard, and I will explain it over here on the whiteboard that how it will work. So here is the OSI model. Let me draw. We have the application layer. We have a presentation layer. We have a session layer. We have a transport layer. We have a network layer. We have a data link layer. And the last one is the physical layer. So these are the 7 layers. This is the sender side, and on the other side we have the destination side, or you can say the receiver side. And we can divide it into application, presentation, session, transport, network, data link, and physical layer. So look at this, the user actually interact with the system on application layer, and it create blocks of data, Then there is encryption and compression of data on presentation layer. Encryption and compression of data. Remember, this block of data actually move in the form of data in the form of block, and it goes to the next level as data, and then a presentation header is actually added over here. This is PH, the presentation header. Similarly, all this will be treated like a data, and then it is actually on session layer, the session header is added. And session header will actually provide information about session ID, session hardware requirement, session start time, session end time, and similarly all those information about this session, it will be here in the session layer. Similarly, all this packet will come in the form of segment to transport layer, where transport header will be added. On transport layer, as you know that we have different types of protocol, TCP, UDP, and RTP, SCTP. These are the protocol which are actually used here at transport layer. And here the transport layer, we are also using an identifier, that is the port number. The port number is actually used for identification of these applications. For identification of these applications, while on the network layer, all this data will come in the form of data, and then we will add the network header. So the network header is actually added over here, and this network header is the IP address of source and the IP address of destination. Similarly, the device working on this layer is router. The router and gateway actually work on this network layer. And over here, it will come in the form of data, and the data link header is added over here. And over here, we have an address that is called MAC address, that is also called the physical address of the node. And similarly, the device working over here is called switch and hub. And over here onward, the data will directly go on the physical layer on the link and will be transferred over here. Another important thing, on this tree layer, we actually call this data as block of data. On transport layer, we call it segment of data. On network layer, we call it packet of data, packets. And here we call it frames on data link layer. While on physical layer, we call bits or bytes. It depends on your protocol, that either it can carry bits or it can carry bytes. So it will pass over here from the switch and then onward to the router. So look at this, when it comes to a switch, then the header till data link layer will open over here. Is make layer is actually used by a switch, and that's why the switch can open the data link layer header, while router actually work on network layer on IP address. That's why the router can open the IP header in this term. And similarly, the data will come forward and will be transferred to the destination node. Yeah. Is there any question? Someone is sending me the message. Is there any question from anyone? Yeah. Minix. If there is any question, you can ask. Now here the data will be received in the form of bits and bytes, and will be transferred over here in the form of frames to the upper layer, then in the form of packets to the next layer, then in the form of segments, and then in the form of blocks to these layers. So this is actually the complete process, that how it takes place. That's why the IP address is checked over here on the router. The MAC address is checked over here on the switch, and similarly over here, the MAC layer is checked over here on the. So moving back to the slide over here, And now you can see over here. Look at this. Transport layer is responsible for low-level network access and for message transfer between clients, including partitioning messages into packets and maintaining packets order, controlling flow, and generating physical address as well. They can also have that where they are, how they control the message, and as I told you about the TCP mechanism to of three-way handshaking, so they can establish the link and decide that what will be shared for how much time in this session. Here is the session layer. It implements session process to process communication protocol as well. That's why it is important that what will be the requirement of session, what is the session ID, what is the session start time, and similarly some other information related to session. Similarly, next we have the presentation layer. It resolves the differences in format among the various sites in the network, and that include character conversion and half duplex and full duplex encoding as well. And next is the application layer. It interacts directly with the user and deal with the file transfer and remote login protocols and electronic mail, as well as the schemas for distributed database. So this is actually the place where the user interact, and after that the other processes start on the data. Here you can say you have the computer A here in this diagram and computer B, and the process actually starts from application layer where the user interact with the system, and then again it comes down to presentation, session, transport, network, data link, and physical layer. This is the data network you can see with the help of which they can communicate. And look at this, the header actually opens, you can see here in the mid, the header actually opens on the network layer. And if there is anyone who is trying to open it to transport, presentation, and application layer, then that is a kind of attack against your data. So the header actually opens till network layer to know about the IP address of source and destination. It opens at data link layer to know about the local address, that is the MAC address, and then physical address, it actually travel on this physical address. So here you can see an application layer, distributed information services, and responsible for file transfer, access and management document and message interchange, job transfer, and manipulation as well. You can further see that there is no dependency on any other layer related to the message processing. Similarly, in presentation, the transfer syntax, negotiation, data representation, and transformation as well. And that's why I told you that all the encryption, decryption, similarly compression of data takes place at presentation layer. While in session layer, they check about the synchronization control and the dialogue control with the help of different protocols between different applications, while transport layer is actually responsible for end-to-end delivery. And look at this, the end is actually defined as an application on the system. And you can see here in this diagram, look at this, this is your computer, and there may be multiple applications open over here. So for example, you have a Gmail, you have a UMKC website, you have a Facebook, you have Yahoo, you have a chat software, and similarly you are also looking at the BBC, are you at looking at the CNN or Fox News. So look at this, we have multiple application over here open in these systems. There are more than 5 applications working on this system. So how we can identify these applications? We identify these applications with the help of port number. And this port number is actually the software port number. We also have a hardware port number, but this is actually a software or application port number. We also have a hardware port number, but it is different than this one. So this is actually the way we are looking at it. Yeah, next again you can see the data link layer header will be removed, then network, then transport, then session layer, then presentation application, and then he will actually get the final message. Similarly, there are different protocols, one working on each layer. Like in an application layer, we have the HTTP protocol, we have the DNS protocol, we have the telnet protocol, we have simple mail transfer protocol, and we have FTP protocol, file transfer protocol. This telnet protocol is actually used for remote accessibility. If you want to access a system from remote area. Similarly, on presentation layer, it is not defined, but we have different compression and we have different so we actually have these protocols on it, and I think there's some confusion with few students. Similarly, for session layer, we have not defined protocols, but there are many in use. On transport layer, we have TCP, we have UDP, we have SCTP. On network layer, we have IP, we have IPX, and we have SPX protocols. IPX and SPX protocol. On data link layer, it is actually data link layer, we have different types of control protocol, but it's not defined over here. And our physical layer, we also have protocols for physical accessibility. Similarly, we have failure detection. As I told you in last class, that there may be some fault tolerance mechanism as well, that they can handle your system in case of any failure. Detecting hardware failure is difficult in the system, and the reason is that there are too many hardware in the system, and that's why it is very difficult for us that where where it is, right. Assume site A and site B have established a link, a fixed interval, each site will exchange NIM up message indicating that they are up and running. Assume site A and site B have established a link and a fixed interval, each site will exchange IM up. Look at this, this will be a kind of broadcast message in which the system is informing its other friends or other counterparts who are involved in this distributed system or in the network that I am available. If, for example, if there is any failure of this message, and the nodes didn't receive or didn't listen from that node A or B, they will actually write it that this system is down in their memory, and they will not send any packet to them. If site A doesn't receive a message within the fixed interval, it assumes either the other site is not up. Look at this. As I told you, if they doesn't receive a message within the fixed interval, it assumes either the other site is not up or the message was lost. The message is lost, for example, and it is not available. Site A can now send an "Are you up?" message to site B as well. So you can also send a message to site B and ask site B that either site B is available or not, and you can wait for its response. And how long you will wait for his response is normally the RTT time. The RTT time is round trip time, and that is actually that you go to and access the destination node, or you send a packet and it approach the destination node, and then onward it return back and reach the sender node. Site A can now send an "Are you up?" message to site B by confirming that either he is available. If site A doesn't receive a reply, it can repeat the message or try an alternate route to site B. If site A doesn't receive a reply, it can repeat the message or try an alternate route. You can see over here, if site A doesn't ultimately receive a reply from site B, it concludes some type of failure has occurred, and there are different types of failure. Number one, site B is down. Number two, the direct link between site A and B is down, and there may be an option of alternate link. The alternate link from site A to B is down, or the message has been lost. So there are different possibilities that you can decide based on that what will be the possibility that he didn't receive the response back from that site, and that can be the site failure, that can be the link failure, or that can be the loss of message because of the collision with someone on the link. However, site A cannot determine exactly why the failure has occurred. Look at this, there is always a probability that what is the maximum probability, or which option may happen at this particular link. So you can see, if you are communicating on a link that is congested and shared by multiple users, then its capacity, then the maximum possibility is that the message is lost. The lost means failure, that is, the message is lost because of the collision with any other node. And if you are actually using a flapping network in which the network connectivity is not very reliable or unreliable, then there may be a possibility of link failure as well. Similarly, the robustness or reconfiguration, when site A determine a failure has occurred, it must reconfigure the system. When site A determine the failure has occurred. And as I told you, that the robust system is just a fault tolerant system. If the link from A to B has failed, this must be broadcast to every site in the system. If a site has failed, every other site must also be notified, indicating that the services offered by the failed site are no longer available. And look at this, with this message, you are actually stopping all those requests which are going toward that direction, which are going toward that system. So you are actually going to stop that system from overwhelming. And that is a very good approach, that you actually stop all those requests at the first point by informing their sender that they should not send any message to that particular user, as that user is no more available. When the link or the site become available again, this information must again be broadcast to all other sites. When it is come back into life and it is available, then you must inform everyone that this node is now available, and now if you want to communicate with him, you can send it or you can share your data with him. There are certain design issues in distributed system. The first one is transparency, where the distributed system should appear as a conventional centralized system to the user. Look at this, there is no visibility to the user from where he is getting service. As I told you, you are connected with the Google server, you are connected with the Yahoo server or with the Facebook server, but you don't know with which server you are connected. And similarly, you are now connected with the UMKC server while taking this lecture, but you don't know that there may be multiple servers at UMKC and you exactly don't know with which server you are connected. So this is actually a transparent approach, that you are receiving services, but you don't know with which you are connected. Similarly, the fault tolerance, the distributed system should continue to function in the face of failure as well. And that is, as I defined it in last class as well, that in case of failure, the the remaining part of the systems are struggling their best to provide services to the user. And scalability, as demand increases, look at this, the scalability terms is actually derived from scale, which means that any increase or sometime even increase and decrease in the system resources, in the number of users, in the number of links, in the number of other resources may affect the performance of system. As demand increase, the system should easily accept the addition of new resources to accommodate the increased demand as well. And cluster is actually a kind of group, a collection of semi-autonomous machines that act as a single system. So they are actually working together with each other and actually taking care of all those activities. So here is the end of this lecture number 1. And now we have to. So dear students, now we will start the second chapter, that is distributed file system. Here is the course outline that we will discuss: the background, the naming and transparency, remote file system, stateful versus stateless service, file replication, and then an example of distributed file system, which is Endio file system. So what is a distributed file system? Distributed file system is actually the file system that supports sharing of files and resources in the form of persistent storage over a network. For the first time, it was developed in 1970s, where the first attempt was made. And later on, the Sun Solaris, the Sun Network File System, became the first widely used distributed file system after its introduction in 1985. So the distributed file system is actually such a file system which provides services to different clients at different locations, and where the data is stored on a network of computers. So whenever a client wants to access data, they can send a request to the server, and it's not necessary that he will receive data from the same server every time. You can see here in this diagram, we have two types of system. One is centralized storage,
where data is stored at a single place. And another one is distributed file system. You can see here we have different types of servers, and they actually work based on request and response. The node or the client which needs some file will request the particular server, and then he will provide the necessary data. Now, distributed file services activity has to be carried out across the network, and instead of single centralized data repository, the system has multiple and independent storage devices. The distinctive feature of distributed file system are the multiplicity and autonomy of client and server in the system. So look at this, they are working together in such an environment that they can fulfill the client and the user requirements. Here are different components of a distributed file system. The first one is actually the service. Service is the software entity running on one or more machine and providing a particular type of function to an unknown client. So service is actually related to the fulfillment of request, addressing the request, and providing the necessary support. Where server is actually the system which provide that service. So service software running on a single machine which provide the services to all clients. And client is actually that machine or a process which requests for something. The process that can invoke a service using a set of operations that form its client interface. And client interface of distributed file system should be transparent, not distinguish between local and remote files. So that is important, that the client should not know about that from where he is getting service. He must have a transparency with the other nodes. And as you know, that there are different types of activities one can perform on a file. Like they can create, they can edit, they can modify, they can write, they can read, they can execute, and they can delete a file. So that's why the client should request for something like that. So client and servers, a file server provides file services to the client, and a client interface for a file service is formed by a set of preemptive operations, such as creating a file, deleting a file, reading from a file, and writing a file. So look at this, for which activity or for which right you actually want the access. Here is the data access mechanism from a distributed file system. And you can see that the client sent a request to access data. And for the first time when he requests data, it is checked in the cache of client. If it is present, then it will be provided for processing. But if it's not, then the local disk will be checked. And if it's present there, then it will be provided. But if the data is not present and at the local disk, then the request will be sent to the server. And you can see here, the request is sent to the server, and the same process will be repeated here, where data is first checked at the server cache. If it's there, then it will be presented. Otherwise, the disk will be searched, and then it will be loaded to the cache of the server and will be provided or presented to the user. So here we have another important thing, that is the naming and transparency, that how you can identify a system or a computer. Naming means that mapping between logical and physical object, that how you can map the logical. In many cases, we use IP address as a logical address, while MAC address is used as a physical address in a network. Sometimes we also need a multi-level mapping, where abstraction of a file that hides the detail of how and where on the disk the file is actually stored. A transparent distributed file system hides the location wherein the network the file is stored, and ideally, a distributed file system should appear to its client to be a conventional centralized file system. So it means that the client will not be aware of any multiplicity and the dispersion of file across the server inside the network. He will only get the required file or the required resource as per his request. For a file being replicated in several sites, the mapping return a set of the location of this file replicas. Both the existence of multiple copies and their locations are hidden as well. As you can see here in this diagram, we have file 2, 3, 4, and they have different components. And for example, here file 2 is present with the client 1, with the client 2, with the client 3. So the file 1 is actually at 3 different locations. And now we have to use some mechanism that these clients should not do any change at the same time. They may request for any updation, for any execution to the server, and then the rights will be given based on their request. Here is another important thing in this naming structure, that is the location transparency, which means that the file name doesn't reveal the file physical storage location. That is very important, because if the file name show any location, then it may create some sort of threats for the data of the user. So that's why a location transparency means that there will be no awareness of the storage location of the file from its name. And next one is the location independence, which means that file name doesn't need to be changed when the file physical storage location changes. So whenever you want to change the name of the file, then there is no need that you should change the file physical location. So any changes may be done at any time, but it is not necessary that you can change the location.
So a distributed file system should provide multiple client processes on multiple machines, not just accessing but also updating the same file. Concurrency control or locking may be either built into the file system or be provided by an add-on protocol as well. You can have the concurrency in all file, that any change in any file should be done everywhere that file exists or that file is copied. You should make sure that all the file should be equally updated. It may not happen that a file one stored at 5 location and on 2 location it is updated and on 3 location it is outdated. A distributed data store is a network in which a user store his or her information on a number of peer network nodes. So this is just like cloud, that you are storing data at different location. Most of the peer-to-peer network don't have distributed data store in the user's data, only available when their node is on the network. And this is also the same whenever the server is available, the cloud services are available, the internet connectivity is available, the server is on, then you would be able to access the related resources to that server. Here are some example he is giving over here of this distributed data store, that is freenet, mnet. We have used this Andrio file system, and BitTorrent you are using for different purposes to download different movies, different video or audio file from different location across the world. BitTorrent is very famous for that purpose. GNUnet, similarly, we have the secure file system and the global file system are distributed version control. Or you can have the Groove shared workspace or the Docky. Similarly, remote files access remote service mechanism is one transfer approach, that you can transfer your data based on request to any other location. And as I told you on the OSI model, that telnet protocol is actually used for this purpose to access data from remote location. It reduced network traffic by retaining recently accessed disk block in a cache. And it was also clear in the first diagram we discussed earlier that first, if a user or a client need any data, then they will first access the local cache of that user. If it is available in the local cache, then it will be retrieved from there. Then onward, it will be search at the local dist of that client. If it's available over there, then it is fine. Otherwise, they will request to the server, and then onward will be search in the server cache, then in the server disk, and then it will be provided from there to the client. And even if it's not available at the local server, then the remote server will be accessed. The remote caches would be accessed in this case. If needed data not already cached, a copy of data is brought from the server to the user. Look at this. Is there any question? Okay. If needed data not already cached, a copy of data is brought from the server to the user, and accesses are performed on the cached copy. Look at this, the accesses are actually the operations as well. Like you are reading, you are writing, you are editing, you are executing, you are modifying, even you are deleting. So it will be performed on cached copy, that is cached and on client side. It will not be performed on the original copy that is with the server. So once you have updated this cached copy, then the data will be updated over there on the server side as well, but with the permission of owner, with the permission of server as well. The files identified with one master copy residing at the server machine, but copies of parts of the file are scattered in different caches. So there is possibility that you can have a file scattered somewhere at 5 multiple locations. And because of this problem, the cache consistency problem will raise, keeping the cached copies consistent with the master file. And let me explain it here on the whiteboard for you people. So coming here, this is the main file, that is file 1. This is the server location, right? And we have file F1, we have a file F2. And these are the clients or the client tree. And we have files over here, F1, F2, F3. He has F2 and F3. F1, F2, F1 and F3, F3, right? These are the files. And now look at the data in these files. Here is A, right? Here is X, and here is M, right? So if he has F2, he has X, he has F3, he has this is M, right? M for modern, M. So here is M. Here is F1. So in F1 we have A. Here is F2. We have X. Here is F1 A. Here is F3 M, and here is F3 M, right? Now, if client 1 actually adding here Y in F2, he is adding N here. Here in FA, F1 client 2 is adding B, and here in F2 he is adding Z. Here in F1 client 3 is adding C. Here in F3 he is adding N, and here in F3 client 4 is adding N. So now look at these file with all these clients, and look at these file with all these servers, the parent file. And these files are totally different from one another. Look at this, they are totally different, right? And this is the cache consistency problem. This is the cache have something else here in client. These files have something more data here, and similarly, these file status are totally different on the server side. So look at this. The next, when we will have the server side, we will update these files on the server side, F1, F2, and F3, and these files will now become F1 will have A, B, and C. F2 will become X, Y, and F3 become M and N. So this is actually the main site. Look at this. We have XY, and even he is adding XYZ here in this diagram. So we should also add Z over here. XYZ, ABC, MN, and here we have simply N, and over here he's adding N. So now this is, we should update this record here on the cache. And now if the client want to access this data, client 1 want to access this data, then he will have the updated file like F2 with X, Y, and Z information. And similarly, if he want to access F1, F1 will have the updated information A, B, C, D. And now, for example, if client 1 deleted this C and deleted this Z, so the new status of this file at server will be A, B for F1, and it will be for F2, it will become X and Y. It will become X and Y. So is it clear?
Yes.
Yes.
So this is actually the cache consistency problem. And let me share the screen again. This is the cache consistency problem. I hope it is clear to you people now that how the cache consistency problem may happen over here. And look at this cache location where it is. Disk work says main memory where the cache is. Advantages of disk cache. This disk cache is actually the virtual memory, and it provide more reliability as well, added more reliability, and the cache data kept on disk are still there during recovery and don't need to be fetched again. And there is no need because you will store it at your local disk. As I told you that many website, many software actually store data in your local cache, and whenever you want to access this data, it provide it from your local cache. Advantages of memory cache is also given here. It permit workstation to be diskless, mean you can store data at the server where you want, and you have seen these new systems in many offices that they have a single service and there is no CPU with every system. You have just a screen and a keyboard and a mouse. So whenever you log into the system, you are directly communicating with the server. Whenever you are storing something, you are directly storing it on the server. That is the diskless system. Data can be accessed more quickly and performance speed up in bigger memories as well. Similarly, servers caches are in main memory regardless of where user caches are located. There is no need where the server cache is. What the server cache have is not dependent on the client side caches, as I show you over there, that you have to update everything to the server because the client can crash anytime, and failure of client or if the client goes log off or it shut down, then no data will be available to the user. So there are some cache update policies. So here we have the cache update policy. The first one is write through, right? And write through is that, as we discussed here on the whiteboard. Yeah, this is the server, and here is the server cache. This is the server cache, and this is F1. This is F2, and here are the clients. 1, client 2, and client 3, right? C1, C2, and C3. So actually write through, as we discussed here, yeah, write through write data through a disk as soon as they are placed in the cache. It is reliable, but it is very poor performance. And you can see over here that this is the network link. through which you actually update these files. The write through means that you just write X over here and you have to transfer it over here and will write X here. This is F1, this is F2, and this is F3. You are writing W over here and you have to transfer and write W here at the same time. You are writing 5V over here or Roman 6 over here and you have to update it over here at the same time. There is no delay involved. So look at this, the traffic on this link will increase. If you are, for example, you are going to delete this X, you are deleting this X or this W and you are converting this W into M and this X into Z, then you have to delete it over here and write Z and M over here. So that's why the traffic on these links will drastically increase in this write through operation. And you can do 1,000 times updation of this file and 1,000 times you will be updating this file at the server side again. So we have another approach, that is the delayed write, modification written to the cache and then written to the server later on. For example, you are writing on the client side for 30 minutes, for 60 minutes, and after 60 minutes, you dump all those data on the server side and update all those files. Some data may be overwritten. Look at this, we are overwriting. Instead of X, we are writing Z. Instead of W, we are writing M. And similarly, we can also modify file number 3 as well. So this overwritten operation may not be transferred again and again to the server. Once you are means satisfied that this is the final update in this file, then you should go and access server. Some data may be overwritten before they are written back, and so need never be written at all. This is poor reliability. Unwritten data will be lost whenever a user machine crashes. Whenever a user machine crashes because of electricity failure, because of any hardware failure, so there is possibility that you may lose all those modification, all those updation that you have done in last 30 minutes or 1 hour. And you know that Microsoft Word or PowerPoint or Excel have this drawback earlier, that if you don't save your file and there is any hardware failure or electric shutdown, then you will lose this data. Now this self-storage or self-saving mechanism is added in Microsoft Word, PowerPoint, and Excel and other applications of Microsoft, that they will save your data after a few seconds. The software automatically save your data. And that's why you should not worry by pressing Control S again and again, Control S again and again. So this is actually a threat in delayed write, that you will lose all the updates you have done in last 30-40 minutes. Variations can cache at regular interval and flush block that have been modified since the last scan. So look at this, it is totally a time-based activity, and you can also add this variation here. Instead of 30 minutes, instead of 40 minutes, instead of 1 hour, you can add write on close as well. Whenever you close this file, you will do all the necessary update on the server side. Write data back to the server when the file is closed. It is best for files that are open for longer period and frequently modified, and especially for the programmer, they are modifying file 1,000 times in a single hour, and that's why you should not update the server copies every time with every modification, because it is not still finalized. And here it is also shown here caches and use of caching. There is a network file server and you have a memory cache write through. Memory cache write through over here. Look at this. So it means whenever you change something on the client side or somewhere, you have to update it at the same time. And over here on this side on the workstation, we have a write back mechanism. So whenever you can modify something, you should update it. You can define or you can have a predefined time for this updation, like 30 minutes, like 40 minutes, like 1 hour, like 2 hours, and so on. And similarly, you can also use the third option, that is write on close, that whenever you close this file, then the server file will be stored. There are two types of mechanism to ensure this consistency. Is locally cached copy of the data consistent with the master, that is actually stored with the server? Then there are two approaches. Client initiated approach. The client initiate a validity check. The client by itself is checking that I have not updated this file from the server, and that's why there is possibility that this file may be stored at multiple location. That file may be under execution with multiple clients, so maybe there is a possibility that some other clients have done some modification. And this is just like that you are playing an online game with multiple players. So you have to refresh again and again that what the other player have done, what the other player have done. So you can get all those changes, all those modification done by any other client, done by or performed by any other user or any other client. The server checks whether the local data are consistent with the master copy or not. And similarly, if there is any deficiency, any problems, the server can update it and the client can start this process at the server side as well. The other mechanism is server initiated approach, where server records for each client and the parts of file it caches. When server detect a potential inconsistency, it must react. Look at this. A potential inconsistency can be defined like 50%, like 40%, like 20%, like 30%. Then you have to initiate this approach. Once the server or the client know that now this file is more than 20% modified from the original copy, and these modifications or these alterations done by this client may affect the output or the outcomes of any other user, of any other client, or even on the server side, then they must update this file master copy at the server side. Comparing caching and remote service over here with one another. In caching, many remote accesses handled efficiently by the local cache, while most remote accesses will be served as fast as local one as well. If you are accessing data from a remote location, then there may be some problems like network connectivities, like congestion on the network, and it may affect the performance. But if it is stored on the local cache, then it means you can directly access and there is no dependency. There is no worry about congestion, there is no worry about overhead or dependency on any other system. That's why most of the things are locally cached by the new softwares the programmers are developing these days. Servers are contacted only occasionally in caching rather than for each access. And that's why it reduces server load and network traffic. So look at this, if you are saving everything locally at cache, then you are reducing the burden on server side as well. Like if a server can handle 500 user at the same time, and you reduce this burden from the server, so the server can handle 1000 or 2000 user at the same time if everything is stored locally at their caches. Because in that case, server has to respond at specific time to those clients who has any issue. It also enhances potential for scalability. That's what I told you. That now the server is able to handle 2000 users instead of 500. So this is, you are increasing the scale 4 times. You are jumping from 500 to 2000 with the help of this new approach of caching data at local clients. Are the required data, are the data they use very frequently. And that's why we also have an algorithm based on this, that is frequently used programs, are frequently used processes, are frequently used instructions. So the frequently used programs, processes, R files would stay there in the caches of those clients. Remote server method handle every remote access across the network, and penalty in network traffic and server load and performance that will further degrade the overall performance of the network and the user. If there are more users, then there is possibility that the clients will wait for longer period of time and the server response will be slow. The total network overhead in transmitting big chunk of data is lower than a series of responding to specific requests. And that's why you can modify that. You can, instead of transferring the same data again and again, you can save it there at local cache. Caching is superior in access pattern with frequent writes, and write frequent with frequent writes, substantial overhead incurred to overcome cache consistency problem. You can also handle by updating the caches both at client and server side, and it will provide many benefits to the client and server as well. And we, as we discussed on the last slide, that it will handle your scalability issues. It will also speed up your processing. And similarly, some other benefits here: benefit from caching when execution carried out on machine with either local disk or large man memory. And similarly, remote access on diskless small memory capacity machine should be done through remote service methods. If you don't have any local memory, then every time you will go for remote accessibility. The lower inter-machine interface is different from the upper user interface. Look at this, the communication between these client and servers and among different servers may vary from server to server. Like a server is requesting to another server, a client is requesting to a server, and a client is requesting to a client as well. So there are different types of communication between them. So I think it's enough for today. As the topic is going to change.